Hello, everyone, and welcome to another episode, as the case may be, of Cosmic Pie. I'm Robert Moore, and with me today is.
Not Wayne. I'm Dean Smith again. You might have seen me
I love
before.
it. And we're coming to you live from the wonderful campus of the University of North Dakota. And would like to thank both the university, or both, thank the university, the Department of Physics and Astrophysics, and the College of Arts and Sciences for our ability to come to you live today and preferably every week. And I will start out after that by saying that the opinions that are going to be expressed today are those of myself and Dean, and not necessarily reflect the opinions of the state of North Dakota, the University of North Dakota, right on down the list. They're just ours. So with that in mind, how you doing today, Dean?
Oh, I'm doing pretty good,
Excellent, excellent. Getting ready for the semester?
I guess.
I guess. That's the way I feel about it.
Summer always goes way too fast.
It goes way too fast. Oh, especially here the last little bit. You know, you wake up one day and it's like, wait, 2 more weeks and classes start. Oh my.
Oh yeah, like
Yeah.
you're not ready for it.
You're not ready for it. You may think you are, but you're really not, folks. So anyway, let's see. I know normally when you're with us, we talk about the night sky that we usually can expect, but we covered the summer sky, and it's still summer.
Yeah, I did not want to think about fall yet.
Right.
So we'll get to the fall sky, I think, in fall.
Right. And
So
I will just say, you know, when you're in North Dakota and you start thinking about fall, you think about winter, and we don't really like to think about the winter here.
yeah, I like to think about summer a little early, but
Yeah.
fall. Oh no, that's
And hello to you as well, Mizuho. Good to see you with us again. And so I guess the question then is what are we going to talk about today,
Yeah,
Dean?
so I'm gonna do something different this time. So I was watching your older podcast, well, not like a month ago,
Right.
and you covered the solar system,
Okay.
and I thought, hey, I have a few things to add, and
All
so
right.
I thought I would talk a little bit about some extra things, mainly moons of the outer solar system, and he covered some of those. So I'm a little out of my comfort zone because my background is physics.
Okay.
Rob's background is planetary science, so he can correct me.
Uh, yeah,
So,
but we'll try not. I
but
think you'll get it.
but I'm going to look at bigger scale kind of. I'm not going to get down into mineralogy because I shouldn't talk about
I don't
that.
want to get into
So
mineralogy.
so that's not me. So first I want to talk about. I'm not going to go to any slides quite yet.
Okay.
But when we look at these moons, some of those moons out there are active, and you talked about Enceladus around Saturn. I always get
Right.
Enceladus and Europa mixed up. We'll start with E. Very similar.
And they actually are similar. Yeah.
So, but you talked about Enceladus, and a lot of people before we sent spacecraft out there thought that these moons would be kind of like our moon. They'd kind of just be heavily cratered, not much happening on them. And so, why is there anything happening? Why is Enceladus, Io, Europa, these moons of the outer solar system are active? Our moon, not much is happening. It's
Right.
it used to have some activity. Our moon used to have volcanism.
Used to have volcanoes.
Yeah,
Yeah.
and you can see some of them. I've seen some of the volcanoes on the moon with a backyard telescope, but not anymore. So, in order to have something happening, you need energy. You need an energy source, and so I want to talk a little bit, and this gets more into the physics side, the energy sources that would drive geology, uh, and so there's a few different energy sources, and the original energy source is going to be the energy from formation. And so when these things form, you have accretion, basically have collisions of things smashing into each other. And that accretion is really, it's a conversion of gravitational potential energy into thermal energy. And I'll
Right.
probably say heat, even though we usually say heat as a transfer. A little more friendly language, I'll say heat. So So it heats things up. And so we have this initial, like, the Earth formed, it was molten just from all that energy from the collisions. Then we have some more heat from differentiation. You basically have the heavy elements like iron sinking down and lighter ones going up. And so again, this is basically gravitational potential energy turning into heat. And so there's another heat source. So the planets start out really hot, molten. They have this initial source, and then they start cooling. And so you have heat moving to the surface through convection. You can have volcanism, actually, moving molten rock onto the surface. Then they radiate and cool down. And so over time they cool down. You get the solid crust. There's still a couple energy sources. So the obvious one would be the sun heating the surface. And another big one that a lot of people don't know about, unless they've taken a class on this, would be radioactivity. So there's radioactive elements throughout the interior of the planets, especially the rocky planets like the Earth and the moons. And so there's this energy source of radioactivity. So that slows down the heat loss. And so planets like Earth, Venus, they still have a lot of the heat. They still have a lot of melted interior. The moon is basically frozen. It's lost its heat. And so activity is basically, died off on the moon. And so why is it that our moon is basically dead, but some of the moons around Jupiter and Saturn are active?
Are still really
active. Not just recent, right? And when Voyager went by, some of you would say, well, there was at least recent activity. Now we know there's active activity. And so there is another heat source. And so this is going to get into kind of the main topic. There's another heat source, is tidal heating. And so you've heard about tides probably on the Earth. And tidal forces occur because we have this gravitational force acting between two different bodies. And that force depends on distance. And so in the Earth's case, and we can probably go to the tidal force slide here. And so in the Earth's case, we have the moon pulling on the Earth, but it pulls on the near part more than the far part. And so this tidal force basically has the effect of stretching and squeezing an object. Now these tidal forces are more than just planets, and you'll probably hear it come up. Galaxies will exert tidal forces on other galaxies and rip them apart. Black holes will exert tidal forces on stars and rip them apart. So tidal forces are an important thing.
And they can be major.
Yeah.
They can be a major thing.
So from the solar system out to black holes, in black holes we call it spaghettification. It'll actually stretch you out. And so this is an important idea here, is tidal force. And it basically comes from the fact that the gravitational force depends on distance, and it's distance squared. So it can be a major difference. So stretches and squeezes. And so for the Earth, we have the effect of tides. And so where we have the long arrows on this picture, we would have high tide here. So the Earth exerts a tidal force on the moon. Now there's no water on the moon. But it did have the effect of changing the shape of the moon a little bit, and it locks the moon. We call it a tidal lock, and that's why we have the near side of the moon always facing us. And so it's tidally locked. And this happens with a lot of the moons of the outer solar system. So if the Earth is able to tidally lock the moon, Jupiter and Saturn easily tidally lock their moons. And so the same thing happens there, is the near side, the side of Io or Europa that faces Jupiter is always at the same side. So now how does this...
I'm going to step in there and go, there are other types of tidal locking, because Mercury is tidally locked to the sun, but it's in what we call a 3-2 resonance instead of a 1-1 resonance. And what that means is Mercury turns on its axis twice, in the time it takes it to go around the sun 3 times. So there are other types of tidal
Oh, right.
locking that can happen. But the most common is 1-to-1, where one side of the smaller body stays facing the larger one. And actually, due to transfer of angular momentum between the two bodies, eventually Earth will become tidally locked to the moon.
Right.
And the moon will be on one side of Earth, and the other side will never see it unless they travel around.
Right.
So,
Yeah. So Earth's rotation is slowing, and yeah, so we're slowly becoming tidally locked. I think it'll take a while.
roughly 4 million years. Yeah.
So
Roughly the rest of the life of the solar system.
so yeah, so it's slowly happening. So and yeah, this tidal locking happens. Planets around stars is one of the things with exoplanets. Some of these nearby planets really close to a star, they're probably tidally locked. And
Right.
one side is facing the star and is really, really hot, and the other side's really, really cold. Not a great place to live.
The only question that we're looking at there is do they have atmospheres? Because atmospheres are really good at redistributing
Yeah.
that heat. Of course, we may not want to land on that planet because hurricane force winds all the time, all day,
So
might
there's
not be
some
the
other
best
problems.
place.
Yeah.
So, yeah. But
So-
sorry.
Okay, so introducing the tidal forces. This is the new heat source in the outer solar system. And so now, of course, the question is, well, if we have tidal forces on the moon and the moon's dead, why would this matter out there? And it matters because Jupiter and Saturn, they have more than one moon. And these moons are in an orbital resonance. So we'll bring up this video, and if we look at Io and Europa, now at the bottom they met. Now Io went around once, now twice, and they meet again. And so Io and Europa always hit each other on the bottom. Europa and Ganymede are going to meet at the top. So there Io and Europa met again at the bottom. Now look at Europa and Ganymede. They're going to meet at the top. Now Europa is going to go around, but when Europa's up on top, Ganymede's on the bottom. But then it'll go around again, and they should match up again. So Europa's going to make a second turn, second orbit. So every 2 orbits of Io, it meets up with Europa. Every 2 orbits of Europa, it meets up with Ganymede. They're just hit again.
Right.
And so this is an orbital resonance. And that constant tugging, so Europa is always tugging on Io at the same spot in its orbit. That keeps the orbits elliptical, and they can't quite be tidally locked. So if you think of this tidal bulge where they're a little bit out of round, that bulge is actually moving around. It's not always in the same spot on Io. And this is a heat source, so we get tidal heating because of this. And it's strongest closer to Jupiter, so that's where the gravity is the strongest. And then it gets weaker as you go further out.
Right.
So
I'm going to point out another
Okay.
factor. We think of these as being moons, so they're small bodies, right? Except Ganymede is actually bigger than the planet Mercury.
right, yeah. So it's like a planet-sized object.
So Ganymede is a planet-sized object. The only reason it's not a planet is because it's orbiting Jupiter instead of the sun.
Yeah, so these are good size objects. So
Yep.
and so now a lot of people expected these to not be all that exciting, but people did predict. In fact, there was a famous paper published in Science, 1979, as Voyager was heading out to Jupiter. There was a published prediction that this tidal heating would melt the interior of Io and it would be geologically active. So there was a prediction that happened. So now when Voyager got to Jupiter and went by Io, we can look at that first Io picture. That doesn't look like the moon, right? So the moon is a heavily cratered surface. And when we look at planets and moons, if there's a lot of craters, that tells us that not much has happened lately. Because geological activity tends to cover up the craters. So not a lot of craters on Io. So this told us that there was at least recent activity. Because because it's very smooth. And then as Voyager was leaving, it looked back at Io, and we have this next famous picture, kind of backlit by the sun. There's this plume around the upper left edge. It almost looks like a moon going behind Io, but that's not a moon. That is a volcanic plume. There's an active volcano on Io, seen by Voyager as it passed by, kind of looked back at it. And so this tidal heating, without that, we'd expect Io to be like our moon, just heavily cratered, nothing happening. But because of the tidal forces and the resonance, do I have the image of the paper? I did not upload the image of the paper.
You didn't get that one to me.
Yeah, I did put it on my screen just to remind myself of it. So I can say it's in Science. It was March 2nd, 1979. And the head author was Peale, Peale. So if you want to look it up,
sorry.
you can get that. But I didn't give him the image. I just kind of made a note for myself in case anyone asked about it. The title was Melting of Io by Tidal Dissipation. So
good title.
Yeah.
Like
so kind of the classic, like, here's a prediction and then an observation, verified.
Verify it.
And and it think it was on, I think Voyager was on the way.
It's science.
A great prediction of this. And then, so Io, because it's closest to Jupiter, is the most active. I believe it's the most volcanic. It's the most active
It's
body
the most
of the solar
active body
system.
in the solar system.
Yeah.
Yes.
So, so there's constant volcanism on there. Next, we'll look at Europa. Europa is the next one out. It's in that 2-to-1 resonance with Ganymede, and also pretty smooth. Now, we don't see the active volcanoes, and I don't know. Have we seen active ice volcanism like on Enceladus?
Not volcanism. There's a big debate as to whether or not we're seeing ice tectonics, as whether there's actual ice plates moving around.
Right, because we see all these cracks. It kind of looks like it's broken up into pieces.
Into pieces. Yeah.
So there's a few craters, but not much. It's a pretty smooth surface. So it looks like there's been some resurfacing. This is this was really the first object, I think, where we thought there was a subsurface ocean.
Right.
And so there's probably a subsurface ocean on here, and some at least recent resurfacing, if not current.
And I will note that we also think there's now subsurface oceans of Callisto and Ganymede, but that's due to Galileo having a magnetometer, and the magnetic field of Jupiter is altered in such a way around Ganymede and Callisto that it's altered in a way that suggests there's a salty ocean, salty liquid, or I should say a conductive liquid inside those bodies. Well, since they're made of ice, what's the salty liquid?
Yeah, and that's
what's
actually
the conductive liquid,
Good point. A lot of these, the composition is different. So Io is fairly rocky, but then you go out, as you get further out from Jupiter, they become more icy and less rock. And so, when you get to Ganymede and Callisto, they're very icy.
Right.
So
you've got a conducting liquid, you've got a lot of water ice. What can be the conducting liquid?
Yeah. So we don't expect on these outer moons to have molten iron cores.
Right.
I'll mention now. I know you mentioned Enceladus in the previous podcast. It's in a 2-to-1 resonance with Dione, so it's a similar kind of thing. Dione's tugging on it every couple orbits, and we have the same thing. The tidal heating there is from Saturn, and then there we actually do see this ice volcanism, or I don't know if you geysers.
More like geysers than volcanoes. But.
So geysers, and that's been observed.
Yeah.
So there's that's active as well, and it's for the same kind of idea. So
looking at Saturn, here's a nice Voyager image.
So this is actually a picture I took.
Oh,
So
that's
I'm
when you
glad
took.
that you thought it was
Oh,
Voyager.
it looked
So-
like Voyager.
So this is
Cool.
probably my best picture of Saturn I took last year, actually. And I'm showing it because of the gap in the ring. So I'm going to move off a little bit from the moons. Look at that gap in the ring. This is the Cassini division. There's this black ring where it's a lower density. There's material in there, but it's a lot lower density than the rest of the rings. So why is there that gap? If something was orbiting in that gap, it would be in a 2-to-1 resonance with Mimas, one of Saturn's moons. Mimas is like the Death Star moon. Has
The Death Star.
the
Yes,
giant
the
crater.
giant crater.
But that material there would be in a resonance with Mimas. Mimas would be tugging on it, making it elliptical. While Saturn's rings they're pretty densely packed. Elliptical orbits aren't going to survive. So the orbits here are very circular. And at anything that's in elliptical orbit, there's going to be a collision. And so here that resonance acted to clear out material in that ring. And so you actually have a visual of that's basically unstable orbits, or at least they would be stable, but they'd be elliptical. And elliptical orbits just aren't going to work here.
And the same thing actually happens in the asteroid belt.
Right.
There are actually bands within the asteroid belt.
Yeah, so there are the Kirkwood. I always want to say Kirkhoff, but
Kirkwood gap.
So
Yeah.
the Kirkwood gaps in the asteroid belt are the same. Now, those aren't as visible, so if you were hovering over the solar system, you might not see them because a lot of the asteroids are in elliptical orbits.
Right.
They're not as densely packed.
Right.
But what we see there are the semi-major axis of the elliptical orbit. Some of the semi-major axes don't show up.
Right.
There aren't asteroids at those orbits because of a resonance with Jupiter.
With Jupiter.
And so
Right.
Jupiter keeps tugging on them at certain points in the orbit. And this has been modeled a while back. And it's kind of interesting because it's not, unless something has changed, but last time I looked at this, it's not a gradual thing. Basically, the orbits become chaotic. And after a while, we get these big spikes, large spikes in eccentricity. And these asteroids end up having higher eccentric orbits, and they cross Mars's orbit. And then if they have interaction with Mars, they can fall in further, and then we get near-Earth orbits. And so we think that this resonance with Jupiter and certain orbits in the asteroid belt, that's our source of near-Earth asteroids. And it basically increases the eccentricity of the orbits, so they travel in. Then they're short-lived. They're probably going to hit a planet eventually.
Right. I was about to say that we're pretty confident that that's where Mars's two moons, Deimos and Phobos, come from. They're captured asteroids that had interactions with Mars and got pulled in. But there's also evidence on Mars, though, that it has had many moons in the past and eats them.
Oh, they collide.
Right. It's
Okay.
like one of the current moons is actually in a counter rotating
Right.
orbit. And what that means is it'll eventually fall into Mars because it's losing energy because of its going the opposite direction from the direction Mars is rotating. Could probably do a whole show on that.
Yeah, I think. Well,
Forget the term that's. But
Yeah. Well, it's interesting because that one, the closer in one, I think it's Phobos.
Yeah.
But might be wrong. That one, it orbits so fast that it goes up. Where the stars will rise in the east and set in the west. Phobos rises in the west, sets in the east.
Right.
So its orbit is fast enough that it goes the opposite direction despite Mars's rotation.
Yes.
So
Yeah. And that's what'll eventually cause it to fall in is because it's going in the opposite direction to the rotation. And that's a losing energy proposition. The tidal forces we've been mentioning are slowly drawing off energy from its orbit, which is causing it to spiral in. So, Mars is apparently a moon eater.
So, Yeah, so I want to mention the Cassini division and the Kirkwood gaps, and so they're related to each other. And again, this is because of this orbital resonance, and so this kind of thing pops up in different places. There's one last thing I want to talk about. It has nothing to do with the resonance or the tidal forces, but it's one of my favorite moons, and so it's okay for a physicist to have a favorite moon.
Absolutely.
And now the reason I like this is this was a mystery object. When I first learned about this, back when all we had was Voyager data, this was a mystery. Now this was a mystery since its discovery. Cassini discovered this. So Cassini of the Cassini division also discovered a lot of the moons around Saturn and discovered Iapetus. He saw Iapetus on one side of Saturn, waited, he expected to find it on the other side, couldn't see it. But then it showed up back again on the original. He could only see it on one side.
This is the two-faced moon.
This is the two-faced moon.
Okay.
So Cassini figured that one side was much darker than the other, actually figured that this was locked. I don't know if they knew about tidal forces and tidal locking, but he figured that one side must always face Saturn, and when it was on one side of Saturn, we were seeing the dark side, and when it was on the other side of Saturn, we were seeing the bright side, and that's exactly what happens. So the leading edge, so if it's coming toward you, you see the leading edge, you see the dark side. So in the picture here, the bottom here, that would be the leading edge, the direction that it's traveling. The bright side on the top, that's the back side that is moving away from. And so when it's on one side of Saturn, you see the dark side. It's about 2 magnitudes dimmer. That was dim enough Cassini could not see it with his original telescope. And then when it's moving away from you, you see the bright side, and he could see it. And so now he later did get a better telescope, and then he was able to see it on both sides. So so this prediction, this was I put it in my notes here somewhere. 1671. There we go. So this prediction was around for 300 years before we sent spacecraft. Just the fact that it was brighter on one side, dimmer on the other.
Right.
So this was a mystery that when I first learned about this, there were multiple ideas of why this might be. Finally, the Cassini spacecraft, fittingly
named for the gentleman. Yeah.
So, and that's what this picture, I'm pretty sure, came from Cassini. I don't think the Voyager ones were this good.
No.
So Cassini orbited Saturn for quite a few years, got some good pictures. The model now is that this has a pretty long day, about it's 79 days to orbit Saturn, and so we think our moon has 2-week-long days.
Right.
So these are really long days. So one side gets really hot, the other side gets really cold. And so ice will sublimate from the hot side, which is the dark side, and then deposit over on the bright side, on the other side. And so there's this, because of this temperature difference, the ice basically is being transferred. It sublimates on one side. Now, once it starts doing that, we have an albedo difference. So once you start doing this, you have the dark side is warmer, it absorbs more sunlight, and it accelerates the process. Now there is a problem. Why would it ever start in the first place if the entire thing is bright? And so something had to start it. And what we think is that leading side ran into material knocked off of other moons. And the leading candidate is a little moon called Phoebe. Phoebe is the next moon out from Iapetus. And so things hit Phoebe. It's a pretty small moon. It doesn't hold on to stuff very well. So material gets knocked off of Phoebe. And there's actually now been discovered a kind of a ring in Phoebe's orbit from material knocked off. It worked its way in. Iapetus sweeps into this material, and it darkened the leading edge. Now we have this differential.
Right.
And so that leading edge, when it's in sunlight, is going to be hotter than when the other side is in sunlight. And this temperature differential then started this transfer.
I was going to comment that, I'll put hotter in quotes because things are still pretty dang cold.
Things are
out
still
there.
cold. Yeah. So yeah. So the dark side, you imagine like in the spring here when the especially along the side of the road, the snow starts to evaporate
Mm-hmm.
and it leaves kind of this really dirty snow
Right.
behind. That's kind of what's happening here.
Yep. Which melts even quicker,
Right.
thankfully.
Once it gets darker, it
Mm-hmm.
doesn't reflect the sunlight and it gets hotter and melts faster.
And yes, this is. I don't think we said it. This is the moon Iapetus.
Oh
Yeah,
yeah.
we've mentioned it a few times, but I don't think we ever
Oh
commented
yeah.
to the effect that this is a picture of that moon Iapetus.
Yep. And so
So
this is an interesting moon that was a mystery for a few hundred years, and now seems to be solved anyway.
seems
At
to be.
least we have a model that makes sense.
Right. So basically, all of this stuff comes back to the whole idea that we started with, which was tidal energy, tidal forces. So that's pretty cool. I think anyway.
Yeah. And it's there's a lot of physics that got applied, to the planet side, even if you might not know the geology. A lot of that was physics and forces and energy.
Right. And that's what physics is about. I mean, we have a few sayings. One of them is interesting things happen at the interface, but that interface can be energy, transfer from one thing to another, or from one site to another. That's usually what we're looking at. So, and speaking of which, we're going to change gears a little bit.
Completely different topic.
Not a completely different topic, but we're definitely going to look at it from a different point of view. And that's because I thought it fitting, given a certain pop cultural phenomenon going on right now and a certain cinematic event, to look at nuclear power and nuclear generation, in particular fission. So the first thing I'm going to ask is what is fission? What do we mean by nuclear fission? And the answer is that generally speaking, fission occurs when we have a large atomic nucleus, something like uranium or thorium, and it either spontaneously or with the addition of a projectile, a neutron or a proton, splits into smaller nuclei. And so this is nuclear fission at its heart. And in nuclear power, what we want is kind of this diagram where we inject a neutron or two or three. And when the target nucleus fissions, we want it to release a few neutrons because then each of those neutrons will go out and hit another target nucleus, which will in turn break down and release energy. And the process continues. So this is at its root what fission is all about. This is what led to Oppenheimer developing something that really probably shouldn't have been developed, but
Someone
it
was
is what
gonna.
it is. He did bring about the nuclear age and nuclear power, which is not a bad thing, but yeah. So this is fission, and it happens because of this diagram. This is what we call the binding energy per nucleon. Describes how tightly a nucleus of an atom is held together, how tightly the little protons and neutrons hold on to each other. And so over here at the left at the bottom is where hydrogen is, because there's one proton. So there's essentially as much binding, there's no binding energy. How can you bind one thing to itself, right? So very steeply, the binding energy goes up as you put in more neutrons and more protons. And so that's what we see here on the left is a very sharp and steep sweep to iron 56. And I'm moving the cursor like you can see it. So iron 56 is what we call the bottom of the hill, because if you notice on the right side of iron 56, the binding energy decreases again. So in other words, there's less energy binding that nucleus together, and releasing it releases some of that energy, splitting it. So over here to the right are nuclei, atoms, that want to slide back to the left to being iron. And to the left of iron, we have hydrogen and the lighter elements that want to come together to be iron. So this is the whole process behind fission and fusion. Is everything in the universe wants to be iron 56. And I love saying that because, this is what causes the death of stars. This is what causes uranium to break down and release energy that, can keep things warm, that we can utilize to heat water and turn a turbine, and all of this kind of thing. And it's all because, in the end, everything wants to be iron 56. And by iron 56, there are different isotopes that are stable of iron, and there's quite a few that are unstable that will nuclear decay themselves. But the lowest energy one, the bottom of the hill, as it were, is iron 56. And I use that analogy of the downhill because this is why things roll downhill. They're trying to go from a high energy state to a low energy state. So everything is trying to go downhill to iron 56. Make sense? Dean's nodding. I hope
Iron
the rest
50
of y'all are nodding.
So this is the most stable atomic nucleus.
It is the most stable atomic nucleus. So in the hearts of stars, fusion has been happening, which we'll get to in a minute, to produce things. But once iron starts forming in that nucleus, iron starts absorbing energy. So it actually cools the core. And at that point, massive stars are dead. They're going to very quickly lose all the energy production in their core because it's all slurped up by iron. And that's the end. A star like our sun won't get there, but this is important for both the release of an atomic energy and, I'm sorry to say, a bomb. Things are sliding from the right side of this graph to the left. And in the hearts of stars, we've got fusion happening, which is things on the left sliding to the right. All right, so what happens in the case of nuclear energy? Well, we have this thing called a chain reaction that happens. So we inject a neutron, it hits a target nucleus, the target nucleus splits and releases a few, in that splitting, releases a few neutrons itself. Now, it's important that these neutrons have enough energy that they can travel around, but you don't want them to have too much energy. Because if they have too much energy, they hit that target nucleus and just explode it, which produces less energy, oddly enough. So you want these neutrons to be released just energetic enough. And you want several of them because not all of them are going to hit another target. So this is the whole idea behind nuclear power. This is in fact the whole idea behind the bomb. So what's the difference? Why doesn't every nuclear reactor become a bomb? I'm going to ask that question to Dean.
Uh-oh. Well, yeah, you hope not. You have to slow this down so you don't get too many.
Right. You don't want too many neutrons in there, as well as not too energetic. So what we do is we surround it by water, and we insert rods of carbon or cadmium because both of those elements, carbon and cadmium, can absorb a lot of neutrons and remain stable. So while we've got uranium or thorium fuel rods in there, we've also between them got all these carbon rods and our cadmium rods. And so when we want to slow the reaction down, make it produce less heat, we insert those cadmium and carbon rods into the block of uranium and surrounded it by water because water will absorb a lot of neutrons. It also does what we want, heats up, turns to steam, and turns to turbine. So between those two effects, water is wonderful stuff. It really does stop a lot of radioactivity. From gamma rays to beta particles to alpha particles. Water will stop it. And so that's how we keep a nuclear reactor from becoming a nuclear bomb, is we simply surround it by water to absorb some of those neutrons, and we insert material that can absorb a lot of neutrons and remain non-radioactive. And so that slows this process down. So there's a classic video that I love showing when discussing chain reactions. and that is this one, where a bunch of mouse traps have a ping pong ball on it, and a ping pong ball is thrown in, and you can see the resulting mayhem. So each trap releases its ball as well as the trap itself flying, which in turn triggers other traps, and the process quickly spreads throughout the room. So this is what's going on in a runaway chain reaction. What we do in reactors is we simply put a blanket over there where the balls don't travel as far, and a lot of them are kept down. So this is a chain reaction. Lovely little demonstration of it. And so this is fission and chain reactions. And, we've got a movie about the father of all of this sort of stuff, or the one who's considered to have fathered it all.
So Barbie, right?
Barbie, right? No. Oppenheimer, yeah. J. Robert Oppenheimer. So the last thing then I think we can cover is that there's two different types of nuclear reactions. As mentioned when I was discussing this, there's fission, which comes in from the right to the left to iron. But there's also this reaction that goes from the left side to the right. And that's the difference between fission and fusion. And so fission is where we are splitting a large atom into two smaller atoms. Fusion is where we're taking a small atom and fusing it into a larger atom. And that all takes advantage of this binding energy business going on. And as you can see, it's why you might hear in the news why we're trying to develop sustainable fusion reactors. Because there's a lot more energy that can be released going from this left side to iron than there is coming from the right side to iron. So there's a lot more available energy to be released in fusing lighter into heavier, particularly hydrogen into helium, than there is fissioning uranium into lighter elements. So that is pretty much what I brought to the table, and that went a lot faster than I was expecting. But I've discovered over the years that my teaching style and my talking style usually depends on a lot of comments coming in from others. And so if you have questions, please throw them out there. But in the end today, we've talked about two different sources of energy, because you mentioned that radioactivity can be a heating source inside of a planet. And in fact, one of the heating sources that fuels the differentiation process, which releases more gravitational energy, is the breakdown of the short-lived radioactive nuclei. Things like aluminum-26, which has a half-life of just a few thousand years, I think. Something like that. Anyway, it releases a lot of heat because it dies real quick.
Yeah, so you're going to get a lot of that early on.
Right. So it keeps the iron and everything molten so that it can fall to the center. Now, uranium doesn't play a big role in this, because uranium actually, it does not like to be with iron. It is not a siderophile, as we call it, element. It does not like to be in with other molten metals. So the uranium and everything actually stayed out in the rock, in the mantle and in the crust. But the other problem with uranium being a good heat source is it's got a half-life of 4.5 billion years. It's just not breaking down that quick. So it's not releasing per mass unit a whole lot of energy compared to aluminum-26 or iron 58, I think it is, or 54. I used to know all of these elements that powered differentiation and everything.
There's a lot of things that you don't think of as being radioactive elements,
They,
but we had a lot of, they're isotopes.
right.
So they were radioactive isotopes
And
that were fairly short-lived, and so they've kind of...
right. And so that all we're left with now is, in fact, the long-lived isotopes, things like potassium-40, uranium, and thorium. and everything else, and potentially bismuth, because there is some evidence to say that bismuth is actually radioactive. It's not a stable element after all. It just apparently has a half-life on the order of the age of the universe. So, I don't know about anybody else. I'm going to call that stable.
Yeah, close enough.
Close enough. So this is, what powered all of that original coming together was gravitational release through thermal energy and a little bit of radioactive help from the short-lived isotopes, which, by the way, could do a whole show on that one too. Because we know what these short-lived isotopes break down into, we can say with fair certainty that during the formation of the solar system, there was a supernova event nearby. Because we've got a lot of daughter elements, the results of the decay of these short-lived isotopes, and these short-lived isotopes could only be formed in a supernova.
Right. Yeah. I know. Yeah. There's isotopes of iron that have been found in the ocean floor, or at least the daughter products of it.
The daughter products,
decayed
right.
by now. Yeah. That's we the only source we know of for those isotopes are from supernova.
So
we have direct. It's kind of cool to say this came from a supernova.
Right. We have direct evidence that these things have happened. And, it's not just us sitting there. I'm sorry I harp on this in the show, but I run up against it so many times that, people doubt, how do you really know that? Well, come join us. Take a few physics classes, take a few astronomy, take a few geology classes. And you find out real quick when you do that we have reasons for making these statements. That it's not just a bunch of guys going, I think we'll say it's this. No, there are reasons for it. So,
A lot of it starts out theoretical,
a lot of it,
or a computer simulation,
Yep.
But then that makes predictions that can be tested. And
Right.
So people look for this stuff.
and experimentalists like myself, we look for ways to test it. When I went to Case Western Reserve, I amused my advisors because we were looking at presses, at anvils that are used to compress objects, samples, to high pressure. And the highest pressures we can do without just blasting with a projectile is diamond anvil cells, which can get up to several, 100 GPa, which is, I think, a few million times the atmospheric pressure. So that's the highest pressures we can do. Well, immediately I'm like, because it's diamond squeezing onto things. If diamond breaks, what else is going to hold up, right? Well, nothing. So they brought this up, and I was like, there's got to be a way of using a non-physical anvil. So immediately I was thinking about high current through a wire, putting a squeeze on things, and I was like, wait, no, that's an impact. That's like shooting it with a projectile. Plus, it would need to be ferromagnetic. And to this day, I'm still sitting here going, I wonder how you could produce some kind of non-physical anvil to squeeze something between and to get to higher pressures. Anyway, I'm rambling at this point. Do you have anything else you want to add, Dean?
Well, on that binding energy slide, did you mention the
I'll go back to it.
The little
I did not mention there's this little spike on the left, and I did not mention it. So what's going on there?
Yeah, so the upper spike there is a helium nucleus, and so the helium nucleus is kind of abnormally stable. And one way of thinking of this, there's a couple ways of thinking of this binding energy, but one is kind of the energy you need to break it apart, and so that helium that's upper spike way on the left, that's a very stable nucleus. So when you're doing fusion, you go from hydrogen to helium. You don't go from helium to the next one, because then there's like this valley, and fusion's always going to want to go up the hill in this the way this is.
This diagram really should be flipped upside
Yeah.
down.
Depends if you're thinking as the energy needed to break it apart, or usually I think in physics we think of potential energy, then it would be upside down.
Right.
So it depends on how you want to think of it. But the way it is here, you want to go up to that more stable, the higher binding energies. And so you're not going to, when your fusion in the stars does not go to the next element, it goes to the next one that has a higher binding energy.
That lower dip is lithium, by the way, and lithium does not like to exist.
Right. I think
It's highly unstable.
most of the lithium we've got is from the Big Bang, I think.
A little bit from the Big Bang. Most of it's actually from cosmic ray impacts.
Oh, okay, yeah.
So lithium does not like to exist at all.
And yet, a good chunk of our technology now is based on
lithium.
lithium batteries.
But this is why there is so little lithium. Is lithium doesn't like to exist. It likes to fuse onto something else,
Right.
like beryllium or boron. And and that's where that curve comes in on the left, that curve leading up to iron 56. That's carbon, that's boron, that's aluminum,
Yeah,
that's
oxygen.
silicon, oxygen, nitrogen. And so
We got a lot of that stuff.
we got a lot of that stuff. And in fact, oxygen and carbon are two of the more stable points on this chart. There's a lot of little jags if you look at this with any kind of get in close to it. And at the more stable jags are elements like oxygen and carbon and, of course, iron. And so it's not surprising when I hear things from the press about how water is found out in the universe everywhere we look. Well, of course it is. Oxygen is one of the most stable, heavier elements, and hydrogen is the most abundant element in the universe. Well, what is water? Hydrogen, 2 hydrogen plus 1 oxygen.
Oxygen likes to combine with stuff.
And oxygen likes to combine
Why we
with
get
stuff.
fires all in
That's
Canada?
why we get fires. That's why we get life. Is there's a lot of energy to be released by letting oxygen combine with things, and no, it's not surprising that we've got a lot of oxygen out there or a lot of water we find out there. It's not surprising to me that we find a lot of carbon monoxide in these cold molecular clouds that are out there. No, this makes absolute sense. These are some of the more common elements that are going to form.
And, organic chemistry is all carbon and hydrogen.
Carbon and hydrogen. So anyway, we're winding down here a little bit, and so I want to go to the last thing. If you're interested in the sciences, if you're interested in the things we talk about, please consider joining us here at the University of North Dakota. And in fact, you don't even have to join us physically on campus, although we like it if you do, because there are a lot of programs that are completely online here at the university. There's over 120 completely online degree programs. And so you can you can join us here at the University of North Dakota without dealing with the weather, the winter of North Dakota. But at the same time, I have to say, I've been here for 2 years. It's not that bad, folks.
And you're from a much warmer climate.
And I'm from the South. So I'm saying it's not that bad. You just got to bundle up and dress appropriately and everything's fine. So, anyway.
And I teach one of those online courses. I
I didn't know that. Okay.
So it's a introductory astronomy of all things.
Okay.
That I teach is enroll anytime. So you can basically enroll whenever you want. And once you start, you have 9 months to finish. You actually have longer. So it's a little more relaxed.
I'm glad we talked about this because you're the first one that I've talked to that actually teaches one of these classes.
Yeah, so you got 9 months to finish the class. It's a little more relaxed than a semester class.
Okay.
So you can fit in with your schedule. Good chunk of my summer has been correcting homework because it trickles in all year long.
So there we have it, folks. Listening to Dean here. Come join us. Have a good time. Enjoy a few classes. Learn a few things. So anything else?
I think we're good.
Okay. If not, I'm going to wrap the show up. I'm going to have a quote because Wayne started that and we kind of like doing it. So today's quote, or this show's quote, is going to be, "There must be no barriers to freedom of inquiry. There is no place for dogma in science. The scientist is free and must be free to ask any question, to doubt any assertion, to seek for any evidence, to correct any errors. J. Robert Oppenheimer. So there's a nice quote besides the really famous one, I am become death, destroyer of worlds, from Oppenheimer. So he wasn't just a one trick individual, folks. Anyway, on that note, I hope you have a great day. Thank you for tuning in. We'll see you next week.